All right, welcome back. Now we're going to combine the labs before where we did content-based and collaborative filtering based recommendations, combine it together with a neural network in a hybrid recommendation system, using once again the Google Analytics data. First, we're going to pre-process our data to combine this together, and then we're going to create our combined model. So first, we're going to pre-process our data using BigQuery and Cloud Dataflow to be used later in our neural network hybrid recommendation model and in the next notebook. Apache Beam only works in Python 2 at the moment, so we're going to switch to the Python 2 kernel. In the above menu, click the drop-down arrow and select Python 2. We're going to first switch into our Python 2 environment, uninstall Cloud Dataflow, and reinstall Apache Beam here. Don't forget, once you're done with this step, to reset the notebook session kernel so that way all this can be pulled into the current session. As always, we're going to import our OS and our cloud training demos here for our project in our bucket, and we're going to have that set to our environment variables, change as needed. We're going to set our project in our compute region, and now we're going to create our ML dataset using Dataflow. Remember here, we're going to be combining the user and item embeddings learned from the Walls Matrix Factorization Collaborative Filtering Lab that were extracted from our estimator, and we're going to combine that with our content-based features such as title, author, category, for instance. Okay, so we created our hybrid data set query here using a couple CTE tables to do a little bit of the work for us. So we're pulling out the full visitor ID here, the content ID, the category, the title, the authors, an array here of when users looked at this content, years and months, and any other custom dimensions. From there, we're going to process this a little bit within BigQuery. Remember, you can do pre-processing within BigQuery itself. We're going to use as our label, because remember, this is a neural network, it's supervised learning, we need to have a label, something to predict. And we're going to be using this next content ID to predict. We're going to try to predict the next thing that this user should read. And for training, what they actually did. So that would be our label, and then some of our input features are going to be visitor ID, content ID, their category, the title, the author, and then the month since the epoch. The epochs usually started from January 1st, 1970, just to try to get like some kind of date range, supposed to have context out, what possibly could have been going on at the time in the world when these people were reading. Maybe that's going to give some variance on why people chose what they did to read. All right. From there, we're going to have our final function where we're going to pull all that in and make sure that's all the right data types and replace any nulls in case there's any strange nulls. And we're also going to combine this with our user factors and our item factors. When I train this using a number of embedding dimensions, my latent factors, as 10. So that's why I have 10 for users and 10 for items here. But if you chose a different number, you'll have a different number of things to bring in. Okay? I also am going to create a hash ID here so that I can do good sampling on to have good repeatable results. And I have to join with my user factors that I pulled out of my estimator and I imported it into BigQuery. And likewise with my item factors. Okay, so let's look at what some of these look like. As you can see, I'm dumping this BigQuery query and putting a little limit on here so I don't have millions and millions of records going into my data lab. I'm going to put it to data frame. And you can see here's my label, next content ID. Once again, it's a big integer. Visitor ID, a really big integer. Content ID, the current content they're on. So this is the current content they're viewing, and this is the next thing that person viewed. The category, news, etc. The title, these all look to be in German, so that'll add a little bit of complexity for those non-German speakers out there. The author of that article they read. The month since epoch, so that way we can tie it a little together in time, so perhaps what was going on in the world at that time when they were reading it. And then our user factors and our item factors. Okay. Do it at describe so we can kind of see some of the statistics of this. The averages and all. These are just of our numeric columns, as you can see, just our user factors. Okay, and our item factors. And now I'm going to call Apache Beam to do some more pre-processing. I want to create sharded files in this case, CSV files. So to do that, I'm going to create my CSV column name. So it's going to be next content ID, my label, and then my features, visitor ID, content ID, category, title, author, and the months since the epoch. And then my factor columns, I'm going to create a list of these, this list comprehension, 2 of them in fact, one for user factors and one for item factors, looping across all 10 of them for each. Remember, this 10 will be a different number for you if you use a different latent number of factors in your collaborative filtering model using walls. So I'm going to write out the rows for each of my inputs. So I do have to be careful here with my encoding since I do have some German characters in there that might be special. So I need to use a UTF-8 encoding here. Otherwise, just casting it to string, you might get some errors. And same goes for doing my other features from factor columns. When that's all done, I have one long string with commas delimiting everything. And I'm going to yield it all out into one big string for every table row that gets pulled in through this row dictionary. All right, now I'm going to call my preprocess function, and I'm going to pass in whether I'm in test mode to use local preprocessing, or not in test mode to use the full power of the cloud, autoscale, elastic, take advantage of that. I'm going to create a job name, and I'm going to determine where I put these things. My output directory for local will be local to my data lab, whereas if it's not a local training and I'm using the power of Cloud Data Flow, I'm going to have it put into Google Cloud Storage. All right, set some options here, and then I'm going to say if in test mode, direct runner, else data flow runner. All right, I initialize a Beam pipeline here using my options and the runner that I designated here. And I'm going to pull my query in, and my query is going to be the hybrid data set from above with those CTE tables and that final feature set with my label of next content ID. If in test mode, I'm going to concatenate on a limit here so that I don't pull in too much data. And then I'm going to create a loop. So for training and evaluation, I'm making both data sets right now. So if I'm training, I want to take the modulo of the absolute value, the hash ID. Remember, we have to take modulo of positive numbers here. So since the farm fingerprint can create negative numbers, I want to be able to take an absolute value of that. And I'm going to break it into 10 buckets. I did some analysis beforehand just to verify that this is a good sampling, and each bucket was approximately 10% of the data. So therefore, I can take less than 9, so I'll get values 0 through 8. And for the last bucket, my 10%, I'm going to put into eval. You can choose, obviously, different splitting. Maybe you do an 80-20 split rather than a 90-10 split. It's up to you. So now I take that initial pipeline I created for each training and eval, as you can see here when I pass in the step from this list that I'm enumerating through. And I'm going to read from my BigQuery source using my query using standard SQL. From there, I'm going to call a flat map to CSV, and then I'm going to write out my CSV from memory for each of the worker nodes into my file at the output directory I designated. And that's it. I'm going to run the job, and I'm going to call my preprocess to call that entire function off, and it'll create my graph in Cloud Data Flow and create all these features for me. As you can see here, I want to move it over just to do some local checking here. And let's look inside. As you can see, I have 3 rows. I'm doing a head on this. And you can see that I have, here's the next content ID, user ID, current content ID, the category, the title, the author. It could be none in case there's no author. The months since epoch. So this is 503 months since January 1st, 1970. And then the 10 user embeddings and the 10 item embedding values. All right, and that's the same for eval and all the trained sharded files we have here. It made 3 of them in this case. All right, I also want to create vocabularies using Dataflow. So I'm going to read from BigQuery, do some pre-processing, and I'm going to write it out to CSV files. Okay, so we're going to write out vocabulary files for our categorical features. So here I'm going to create a query. I've put some values in here that I can then replace depending on the vocabulary I want to generate. And I'm going to do a group by on there so I get the unique list. I'm going to create another Apache Beam job. I'm pulling this in where I'm going to do a group by, as you can see. That's what this is going to be named as, group by. So that's my column name. All right, so I'm going to do that. And make sure you get the encodings again, because in case you have any weird things in category or title or author, any of these other features we could possibly find vocabularies of, we want to be able to handle those unique characters outside the standard set. All right, I'm going to call our preprocess as before, except now we're going to our vocabs folder, since this is not our features, these are our vocabularies. And I'm going to call, as before, my BigQuery. I'm going to write it out to my text file above using my function I created up here. And this will create my vocabulary list. And then I write it out to my text files with the associated name that gets passed in. To look at how I call this vocab list, I pass the index. This index goes here up in the query, right up here, so it replaces the index value. So that way I get the correct piece of content from this nested table. Content ID is number 10, category is going to be number 7, and author has an index of 2. All right, so these are the 3 vocabularies I'm going to generate to get each unique one. Also, I want to get the vocabulary count from the length of vocabularies. To do this, I can get the count to text for counts. That way I can count the number of unique words in each vocabulary. And also I might want to get some aggregates like means or medians or maxes, mins, for instance. So I can create a mean to text that'll write out the mean value from a query. Okay. Everything else is pretty much the same, except now I'm putting it into a vocab counts folder instead of vocabs. But everything is more or less the same here. I create a function called vocab count where I pass the index of the thing I want to count or aggregate, and then the column name. So that way I can create that in the file name. I create a query here where it's a simple, for vocab count, it's just a simple count star as count number. So I'm grouping by over the entire table and just counting all the rows for that vocabulary that I pass in right here. Okay. As before, I write it out to a text file, vocab count, where I replace, depending on if it's category or content ID or author, I replace that there. Also, if I want the global column mean, here it's very similar, except instead of doing a count star, I'm doing an average, where I'm casting it as a float. For instance, if it's my mean epic months, I can figure that out by replacing these right here with my format. Call off the beam job, and that does its thing. Down here, if you want to do a vocab count, I'm going to call that function with the index for content ID, the index for category, and the index for author. To forget the global column mean, I want that for months since epic, so I'm going to use this later on as my default value. In case there is a null for months since epic, I will use this value rather than setting it to 0 or something else. I will create my job, run it, and then I'll call all of that, all above with my preprocess call, and I'm going to do false. So therefore, I'm going to launch a Cloud Dataflow job to create the whole graph, auto scale, all that great stuff to build these things. As you can see here, I can pull these in to look at the head of these. Here's my vocabs. So here's the top 3 things in my vocab for author. Here are the 3 authors' names. I also have it for categories. So it looks like there's 3 categories listed here: lifestyle, stars and culture, news, and also 3 of the content IDs. My counts here will tell me how many I have of each of those. So it looks like my vocabulary for author is only 1,103 unique authors. And category is only 3. So this was apparently all of the categories in the table. Content IDs, looks like there's 15,634 unique pieces of content in my data set. And then lastly, the months since epic mean, looks like the average is 573.6. So we'll use this in the next notebook to train our model, now that we have all of our data preprocessed. Moving to that notebook, we're going to now build our model, and then we're going to train it. Okay, we're going to train it locally. We're going to make a module and train it locally again to check the module is correct. And then once that's set, we're going to send it off to the cloud, do a small training, and then we can create some hyperparameter tuning to then try to find the best values for some of the things that we're going to use. And then lastly, now that we know the best hyperparameters, we're going to plug that in and do a really big cloud job to have a good training model. All right. For this, since we're going to be using titles, we're going to embed this. So we're going to use, rather than trying to learn our own embeddings or pull them in another way, we're going to use TensorFlow Hub. It makes it much easier just to point to an embedding, and it will load it in, and we can train from that. Okay, so first you're going to install that and make sure you have your kernel to 3 now, because we're no longer using Apache Beam. We want to use back to Python 3 since that's where things are going. Okay, so make sure you change that and reset the notebook after you do the pip install to make sure that it's all inside this current environment now. Import everything, set your project bucket region, put that into your environment variables. Don't forget to import TensorFlow Hub since we'll be using that. Set your project and your compute region, of course, and now we can get to actually building our model. So the first things first, we want to pull in some of our global variables for counts, for instance. So with that, we can import a file IO from TensorFlow's library. And to do that, we can point to our vocabulary count files and our means. So here's content ID, reading it in. Great, we now have it within scope, the actual number, 15,000 something. Same for categories, so now we have 3. And author, we have the 1100 in here. And then here's our mean month since epoch. It's going to be 573. So now we have to determine our CSV and our label columns here. So we have our non-factor columns. This is our non-user factors and item factors from collaborative filtering. This is essentially going to be our labels and our content-based features. So here's our label, next content ID, which we set down here as well, our visitor ID, our content ID, the category, the title of the content, the author of the content, and the month since epoch that this was interacted with. As a little bit of context. We also create our factor columns here. Okay, so we're going to have our user factors, all 10 of them, and also our 10 item factors. Our CSV columns would be the combination of our non-factor and our factor columns. We also need to set our default values for each CSV column in case we don't have the values for them when we read them in. Remember, it's a list of lists, so for each one of these are all strings, so this will be called unknown. And mean month since epoch, we're going to read in from above, right here. So we'll replace it with the mean rather than with 0. Our factor defaults are going to be a list of lists, and we're going to create a list comprehension here to do it in a little fancy condensed way for users and for items. And just like before with the actual keys, we're going to concatenate the non-factor defaults, that list, with this factor defaults list to get all features in there. So we have our standard CSV input function, not much to go through here. So we have decoding, creating our features dictionary, creating our single label tensor. That gets called by first getting our file names, creating a data set that we're then going to map our decode CSV function onto. If the mode is training, we're going to have a indefinite number of epochs. We're going to actually use our train steps to determine how many times we train rather than how often we read. And of course we want to do a shuffle so that way things are nicely split and we won't end up in any strange area parameter space overtuned in that respect. Else we're going to have 1 epoch and no shuffle if we're doing evaluation. We're going to repeat and we're going to batch it up so that way we can return and then return our input function. So here's some new stuff. We're going to create our feature columns using our read-in features from our input functions. So we're going to create our column ID, our content item ID column here. It's going to be categorical with a hash bucket. Just in case there's any new content IDs that might come about, we want to be able to have some room for there. So we're going to increase that size. We also might want to embed this, because remember this is a deep neural network, so we need to make sure we have dense columns here. We can't have sparse columns going into there. Not only is it not allowed, but too many zeros could end up killing our network since there'd be too many 0 activations, and therefore the gradients would also become 0. And therefore our model would just not train, and that's not good. So we're going to embed it. We're going to pass in our categorical column here, and we're going to give it the dimensions, basically how many dimensions we have that you want to set at command line. We're going to also create our category feature column here. It's going to be categorical. It's going to use our vocabulary file from before, so it's going to read in the full vocabulary. And we're going to have an out of vocabulary bucket here, just in case new vocabularies come along, they can end up in that bucket. We have to convert it, once again, into a dense column, so that's what we're going to do with the indicator column here. So it's going to pass the categorical we created and call indicator to create our indicator column. Next feature is title. So title is going to be using TF Hub. So we're going to call TF Hub. It's going to be a text embedding column here. We're trying to embed the title text. Okay. The key is going to be title. It's our raw data's key. The module spec here, I'm pulling this model here. It's going to be using German because these are German titles. Otherwise, it'd be EN for English, or other things, ES for Spanish and stuff. It's going to be a 50-dimensional embeddings. There's also a 128-dimensional one. You don't want to go too big because you might overfit, but don't go too small because you might be underfit. So you define what works best for you. We're going to have with normalization here to try to get better training. And we're going to set these to false trainable, so that way these will be fixed. And we're just going to use these embeddings to convert our titles into numbers rather than trying to fine-tune these at all. But if you wanted to and you had enough data, you could set this to true to try to get some better results. We're going to take our author column. It's going to be a categorical column with a hash bucket. We're going to use a author as our key from our raw, and our number of authors, and we're going to add one in here in case author is none, in case we had a missing author. But remember, that's categorical, so we need to embed it into a lower dimensional representation that's specifically dense that can go into a DNN. And we're going to do that using an embedding column here with a number of author embedding dimensions that you create at command line. We're also going to create some boundaries for our month since epoch boundaries. So we're going to go 400 as our min, 700 as our max, and we're going to move in steps of 20 for our buckets. Okay, so we're going to pull it in raw. It's going to be a numeric column, right? It's a float, so we're going to use numeric column. But we're going to bucketize that, okay, using our boundaries that we created. So here's our source column, our source feature column now, and here's our boundaries we created using that list. We also might want to cross some of these. So we want to cross our categorical column with our bucketized months because perhaps certain categories were more used during certain months because certain things were happening in the news. So it might be a useful feature. So we'll use a cross column on these two categorical features, right? They both have to be sparse. And we're going to have a hash bucket size of the number of boundaries possible with the number of categories plus 1 in case there's any out of vocabulary. But remember, this right here is sparse, so we have to create a dense layer. So we're going to use an indicator column to basically create dense out of this crossing. Last but not least, we can't forget about our trained walls model that created our user and item embeddings. So we're going to read these in as numeric columns. We're going to use them as floats, and that's as much as to it. Finally, we're going to create our total feature column list. It's going to be all these features combined together, as well as our user items factors and our item factors, and we'll return that from the function. All right. Now that we have that, we're going to create our model function. Okay, so from here, the to-dos, what you were supposed to have done, you need to create an input layer for your neural network, create hidden layers of your neural network, and also create your output layer of your neural network, all using the correct things and linking to our labels correctly, which will be next content ID. To do that, simply would pass in as a parameter here. Remember, in custom estimators, you want to use the parameters is essentially your window, your portal into the model function. So it's a dictionary, so I can pass in many things. So for instance, feature columns that we created above, I'll pass in and I'll use that in my input layer. Okay, and these will be my features. To create my hidden units, I'm going to loop through the hidden units that are passed by command line and create a loop, and don't worry about renaming. These will automatically rename themselves to net 0, net 1, net 2, so that way we don't have to worry about any collisions here. It'll pull the units out of the list that I provided, and of course we want nonlinearity, so use a ReLU. Use other things if you want in case you're getting problems like ELUs, etc. Lastly, our final layer is going to be our dense layer, where we're going to take the final hidden layer as our input, the number of classes, since we're trying to predict which next content you should read, okay? So it's going to be the number of pieces of content from that vocabulary, and we're going to have no activation here, okay? Because these are our logits. We'll get to predictions in a moment. Now that we have our logits, we're going to find the predicted class indices based on the highest logit, which you can think of, if I squash it down with a sigmoid or a softmax, it's going to be the same value regardless if I use logits or not. So I find the argmax of my logits along the final axis. We don't want to do axis equals 0 because that's going to be batch size, and we don't want to choose that. So this will find us our predicted classes for each example in the batch. Okay. Then we're going to read in our content ID vocab to get our content ID names. And we're going to gather the names with the indices. So this tf.gather, using the parameters of the column ID names, we're essentially just creating a mapping from predicted class index to the name. Therefore, we can return the names, which might be more useful to a user rather than some random enumerated content ID. Okay, if in prediction mode, we're going to create a predictions dictionary returning the class IDs, the class names, the probabilities, which come from a softmax. That way they're normalized probabilities, so the sum of them all should equal 1, and the logits. From there, we create also export outputs, so that way in case we want to actually create an exporter and a serving input function to send it out, which we'll be doing soon, we can actually serve predictions to this model and have predictions get passed back to us. All right. If we're all done with predictions, we can return the estimator spec with the current mode, which will be predict, the dictionary we created here for predictions. There should be no loss, no training, no eval. Remember, this is prediction mode here. Okay. And then our export outputs. All right. So that was an early return. If you have survived this far, you are not in prediction mode. You're either training or evaluation. So let's see what we do from here. So we're going to create a lookup table using our content ID vocabulary that we pulled in from before. Okay, so we're first going to pull in our content ID vocabulary and create our vocabulary file to be used in our index table. Okay, from here we can quickly look up the mapping between the indices and the actual names of the content, the content ID, which is that long integer. Okay, to do that we use table.lookup, and the keys are going to be our labels. All right, so now we're going to compute the loss on this using the sparse softmax cross entropy, since this is classification, and our labels, which are the content ID indices, and our probabilities are mutually exclusive. So now that we have this, we can use sparse softmax cross entropy because we are going to choose our labels, which is going to be, it's mutually exclusive, so it has to be either I read this content or I read this one. You couldn't have read a mix of the two. So that's why we can use sparse here, because this label is just an index of the ID, which came from our table lookup here. All right, we're going to create some accuracy metrics here, accuracy and also the top K accuracy, so that way we can see how accurate the top 10 predictions were. Some eval metrics, some scalars, right? This is a custom estimator, so if you want to be able to see these things in TensorBoard, you got to write some custom scalars. So we'll write these out. All right, and if we're in evaluation mode, we're going to write out an estimator spec with the mode, no predictions, a loss, no training, this is evaluation mode, the eval metrics, and no exports in this case. That's another early return. So if you're still with me at this point, we're now going to be doing training, because that's all that's left. We've already filtered out the prediction mode and the eval mode, so now we're in training mode. So just to make sure, we're going to have an assert here to make sure that we're in training mode before we do any changing, because we don't want to change accidentally the weights that we've trained of our neural network by accident by being in the wrong mode. So we're going to create an optimizer here. It's deep neural networks, or Adagrad works great. You try Atom or other things, and we'll pass it our learning rate. Finally, now that we have our train opt created, we're going to minimize our loss that we set above and set our global step. We're going to return the training estimator spec, where we pass mode, no predictions, the loss, training op. Since we're in training, there's no eval metrics and there's no export outputs. There we are. That's our custom model function. Now, if we do want to be able to serve to this model on CloudML Engine, we're going to need a serving input function that we can put in our exporter. To do that, we're going to have our feature placeholders, okay, using our column name and strings, and we're going to go through our non-factor columns. Remember, we're going to skip the 0th index here because that's our label, our next content ID. And at prediction time, you shouldn't have that because that's the whole point of predicting. We're trying to predict what that value is. And we're going to go to a -1 here because we're not going to include the month since epoch because that's a float, not a string. To add that in, we're going to create a new key called month since epoch, and that one will be a float. And that will finish off our feature placeholders for our non-factor columns. For our factor columns, they're all floats. So we're going to have a simple list to add those columns, those features to our feature placeholder dictionary. For the actual features, we want to expand dim, so that way rather than being scalars, they're going to be now vectors. If you were to print out the shape here, it'd be question mark, comma. So they're vectors of batch size. We're going to return our input receiver, and we're done with our receiving input function. Now that all the pieces are assembled, let's create and run our train and evaluate loop. To do that, let's set our logging verbosity to info so we can see some interesting things printed out as it trains. I'm going to have your train and evaluate, where we have the argument dictionary coming in here, which gets passed from our task.py file from command line. We're going to create our estimator here. It's going to be a custom estimator, so estimator.estimator, with our custom model function. Our output directory is going to be passed here. And then our parameters that are going to be passed through that window, that portal that we created. Feature columns, hidden units, number of classes, which will be the number of content IDs, learning rate, the top K, and then the bucket. Okay, that's going to be our Google Cloud Storage bucket. All right, we also create our training spec right here, passing our training input function. So therefore, we're going to have our training data paths, the train key, okay, and then our max number of steps, which will also come from command line. Our eval specs going to be using our eval input function, so make sure you have your eval data paths here. We're going to have no eval steps, so it'll just do the entire file. Since the number of epochs was set to 1, we're going to have these pulled in from our command line, and our exporter is going to be here. Okay, so it's going to be our latest exporter, so every time we make a checkpoint, we're going to export a saved model. And there we go. We call our train and evaluate loop using our estimator, our train spec, and eval spec, as usual. Great. Now we can run the train and evaluate function. So we're going to first set our output directory where we want to train it locally, and we're going to remove that file tree so that way we don't have any collisions or any problems. And now I'm going to create my arguments dictionary. So normally this would come in from our task.py from command line, but in this case we're doing it locally before the module. So we're just going to create this so it's nice and all collected together. And we're going to call our function and it will train. Now that that has worked, you can run the module locally. So we're going to write our requirements. We want to make sure that TensorFlow Hub is installed. Otherwise we're going to get an error when it tries using it. And then we're going to call our module here, our task.py and our model.py. Okay, so we're going to point to our module, our folder, and we're going to point to our pre-processed features for training and evaluation and set all of our parameters, hyperparameters as we had above in the dictionary. Once that has worked and you've got no errors, now you can take full advantage of running on Google Cloud ML Engine to get the full power of cloud and scale out as many workers as you want. As before, we're going to call an output directory. It's going to be our small trained model here because we're going to do a bigger one later. We're going to make sure you start off fresh, and we're going to submit a cloud training job. We're going to have our region, and module name, where our module is saved at so it can bring it to cloud, the package path, where our scale tier, so how big do you want to make this, and then the current TF version. And then all of our normal hyperparameters as before. So if you want to add some hyperparameter tuning, you can write a YAML file. So for instance, I might want to maximize my, my accuracy, for instance, here. You can change the number of trials and parallel trials. And the parameters here, for instance, batch size. I might do a linear scale here, for instance. Maybe my learning rate, these are going to be floats, doubles, so I have a linear scale. Categorical, I want to try different sets, different permutations of hidden units for my DNN portion of the model. And likewise with my content ID embedding dimensions and author embedding dimensions, right? You might have thought, oh, maybe perhaps 10 was a great idea, but maybe actually it was 17. So therefore, by using Cloud ML Engine to do the hyperparameter training, we can actually find the much better values for that. Okay, moving on, you call off your hyperparameter tuning job. Don't forget to include your hyperparameter YAML that we have here, okay? And it will reset all those values and be able to figure out the best ones. And now that you know your best hyperparameters, now we can run the big trained model. And that will run our module and pull it in, and usually you want to use a bigger number of steps using the best hyperparameters that were found before. And that is pretty much it. That is how you will do a hybrid recommendation system using content-based and collaborative filtering embeddings that have been trained using walls and put it all together to get even a more powerful model than each one separately.